We'll start in 1 minute. Today we'll try to finish section 7.8 on the improper integrals. Last time we were discussing this improper integral that has the form 1 over xp dx as x ranges from 1 to infinity. We already computed the one for p equals 1. We know that it diverges for that one. But let's consider the case when p is less than 1. So the improper integral from 1 to infinity of 1 over x to the p dx. We write this as a limit as t approaches infinity of the definite integral from 1 to t, and I'm going to rewrite 1 over x to the p as x to the negative p dx. So let's just look at the integral part without the limit notation. So this definite integral from 1 to t of x to the negative p dx is equal to x to the negative p plus 1 divided by negative p plus 1 to be evaluated from 1 to t. So 1 over negative p plus 1, we can write that as 1 over 1 minus p. And then replace x with t, we get t to the negative p plus 1, but I'm going to rewrite that as 1 minus p, t to the 1 minus p. And then minus when x is 1, 1 to the negative p plus 1 is just 1. So we want to compute the limit of this. And note that since p is less than 1 in this case, subtract p from both sides, 0 is less than 1 minus p, which is what our exponent is. But if 0 is less than 1 minus p, that means the same thing as 1 minus p is greater than 0. And the limit of that expression as t approaches infinity of 1 over 1 minus p times t to the 1 minus p minus 1. Well, since the exponent on t is positive, a positive number, then when t goes to infinity, this limit does not exist. We would say that it equals infinity. So we conclude that in this case, the improper integral from 1 to infinity of 1 over x to the p dx diverges when p is less than 1. So now we automatically know whenever we see an improper integral of that form, if the value of the exponent p is less than 1, we automatically know that it diverges. Okay, the third case, when p is greater than 1, okay, so we're going to start out the same. Let's just go right directly to the definite integral from 1 to t of x to the negative p dx. So this is x to the negative p plus 1 divided by negative p plus 1 from 1 to t. So just like we did before, 1 over negative p plus 1 is the same as 1 over 1 minus p. And we'll evaluate x to the negative p plus 1 from 1 to t. So again, I'm going to rewrite the exponent negative p plus 1 as 1 minus p. So we'll get t to the 1 minus p minus 1. Okay, this exponent, 1 minus p, what can you say about that exponent, 1 minus p? What's the sign of that number? It's negative because p is greater than 1, so 1 minus p is negative. So we might want to write this as 1 over 1 minus p times the quantity 1 over t to the p minus 1, and then minus 1. And then when we take the limit, as t approaches infinity, 1 over 1 minus p times the quantity 1 over t to the p minus 1 minus 1. So in this denominator, t has a positive exponent. And so as t approaches infinity, 1 over that t to the p minus 1 approaches 0. So this limit is equal to 1 over 1 minus p times the quantity 0 minus 1. So the limit exists. Do you see how we can simplify this product here? 1 over 1 minus p times 0 minus 1. Oh, sorry. Boy, you missed a lot, didn't you? Yeah, so we took the limit of this expression as t approaches infinity. And since p minus 1, this exponent is positive, 1 over t to a positive exponent approaches 0 as t approaches infinity. In other words, this denominator approaches infinity, and 1 over infinity is 0. So we get 1 over 1 minus p times the quantity 0 minus 1. Yeah, we can do it in a couple of stages. We can write it as negative 1 over 1 minus p, and then multiply the numerator by negative 1 and the denominator by negative 1, and we can write it as 1 over p minus 1. So that's the value of the improper integral when p is greater than 1. The improper integral from 1 to infinity of 1 over x to the p dx, it converges to the number 1 over p minus 1. So converges. Okay, so always remember, if you have an improper integral, well, if it's from any positive number to infinity, if the exponent p is greater than 1, you at least know that it converges. Okay, let's look at the next problem. Let's evaluate this improper integral. Hey, the improper integral of 1 over 2x plus 1 to the third dx from 1 to infinity. So do you think it converges or diverges? Yeah, I'm betting that it's going to converge. We don't have 1 over x to the third, but we have 1 over a linear expression to the third. So I'm expecting it to converge. But we can determine what it converges to. Okay, so a substitution might help if we assign u to be 2x plus 1. And then we need du. Du is 2 times dx. So 1/2 du is equal to dx. So we're going to replace dx with 1/2 du. We'll replace 2x plus 1 with u. And then we also have to alter the lower limit. So I'll bring the constant factor 1/2 out front. In this original improper integral, the lower limit is x equals 1. But when x equals 1, the lower limit for the variable u is 2 times 1 plus 1, which is 3. The upper improper limit is infinity. When x goes to infinity, so does u. So the upper limit is still infinity. And then we have 1 over u to the third, but I'll just go ahead and write it as u to the negative 3 du. Okay, so all we have to do is evaluate this improper integral. So we can write it as, well, we should write it as a limit as t approaches infinity of 1/2 times the definite integral from 3 to t of u to the negative 3 du. Okay, so just a little bit more arithmetic. So the antiderivative, u to the negative 3 plus 1 over negative 3 plus 1 from 3 to t. So how are we going to simplify this? In this denominator, we have negative 3 plus 1, which is negative 2. So that's like dividing by negative 2. And if we multiply 1/2 times negative 1/2, we can write this as negative 1/4. And instead of u to the negative 3 plus 1, we can write that as, well, that's u to the negative 2, but we can write it as 1 over u to the positive 2. And then we'll evaluate that from 3 to t. Negative 1/4. And then the quantity 1 over t to the second minus 1 over 3 to the second. And now we can compute the limit. So 1 over t to the second goes to 0. So the value of the limit is negative 1/4 times negative 1/9, or positive 1 over 36. The next problem, another improper integral, this time the improper integral from negative infinity to 0 of x times e to the 2x dx. So let's write this as the limit. Well, I'll use a different letter. We could still use t, but I'll use b as b approaches negative infinity. And then the definite integral is from b to 0 of x times e to the 2x dx. So let's just, on the side, let's determine what this definite integral simplifies to. It looks like we need to use integration by parts on this one. So let's let u be equal to x, so that du equals dx. dv equals e to the 2x dx. And what's v? 1/2 e to the 2x. Okay, so this is equal to u times v's. So x times 1/2 e to the 2x. I'll write it as 1/2 x times e to the 2x. We evaluate this from b to 0. And then we subtract the integral of v du. So we have a constant 1/2. So the definite integral from b to 0 of 1/2 e to the 2x dx. Okay, so this is just going to become minus 1/4 e to the 2x, evaluated from b to 0. So I'll just rewrite this part over again. Okay, then in the next step, we'll evaluate all of this. Okay, so when x is 0, we have 1/2 times 0 times e to the 2 times 0, and then minus 1/2 times b times e to the 2 times b. And then we're going to subtract 1/4 times e to the 2 times 0. And then inside this grouping symbol, we're subtracting 1/4 times e to the 2 times b. Okay, then we're going to let b go to negative infinity by taking the limit. This term is 0, so we don't need to write it again. So the limit as b approaches negative infinity, and here we have negative 1/2 b times e to the 2b. We'll go ahead and distribute subtraction, so we get minus 1/4. E to the 2 times 0 is just 1, so this is minus 1/4, and then plus 1/4 times e to the 2b. Okay, now what happens? When b goes to negative infinity, let's do the easy one first, this term on the right. When b goes to negative infinity, then 2 times that number goes to negative infinity. And e raised to a negative exponent that's going to negative infinity goes to 0. So the limit of this term as b goes to negative infinity is 0. We're going to get a constant, minus negative 1/4. And this one, what about this one? We have a product. The factor b goes to negative infinity, but e to the 2 times b goes to 0. So we have negative infinity times 0. what's negative infinity times 0? It's indeterminate. We don't know. So this one is clearly 0, but we can use L'Hopital's rule. So let's just isolate this part, the limit as b approaches negative infinity of b times e to the 2b So this is indeterminate because an infinity times 0 is indeterminate. But what can we do? We can write this as b over e to the negative 2b. Just using a property of exponents. Okay, so if b is negative, negative 2 times b is positive, and so as b approaches negative infinity, the denominator approaches e to the infinity, or infinity. So now we have infinity over infinity, and L'Hopital's rule applies to that. So the way we do that is we compute the derivative of the numerator with respect to b, which is 1. Compute the derivative of the denominator with respect to b, which is negative 2 times e to the negative 2b. So the numerator is no longer affected by b, and this denominator approaches negative infinity, so 1 over negative infinity is 0. So this limit is 0. So this term in the limit becomes 0. So our surviving number is negative 1/4. 0 minus 1/4 plus 0 is negative 1/4. So the value of the limit turns out to be negative 1/4. Is there a way to verify that at least makes sense? That if the limit exists, it has to be negative? Okay, the limits for this improper integral are from negative infinity to 0. So the only time that x is not negative is when it's 0. E to the 2x is positive all the time. And so the integrand is a negative value for x less than 0. So any definite integral, a negative number to 0, will have to be negative. And so the entire integral is negative 1/4. Okay, the next part of section 7.8. This has to do with improper integrals called type 2. Improper integrals of type 2. So suppose a function, in part A, suppose a function f of x is continuous on the half closed and half open interval from a to b. Notice there's a bracket next to a. That means the function f is continuous at a, but with a parenthesis at b, it means that f is perhaps not defined at b itself or discontinuous. Okay, so it's f of x is continuous on a half open and half closed interval and discontinuous at b, then this integral, even though it looks like it's a definite integral, it's an improper integral because f of x has a discontinuity at the upper limit. And so we compute the limit of the definite integral of f of x dx from a to t as t approaches b from below. That minus sign or negative sign to the right of the term b means that t approaches b from the negative side or from below or from the left. And if the limit exists, then that gives you the value of that improper integral. Okay, part B is analogous. Suppose a function f of x is continuous on the half open and half closed interval from a to b and discontinuous at a. Then this integral is improper. Even though it looks like a definite integral, it's improper because of the discontinuity at a. And this time, the limit of the definite integral from t to b of f of x as t approaches a from above or from the right. And if the limit exists, that's the value of that improper integral. Okay, so as we've seen, the improper integral of f of x dx from a to b is called convergent if the corresponding limit exists, and it's divergent if the limit does not exist. Okay, part C. This time, suppose a is less than c, which is less than b, and the function f of x is continuous on the half-closed, half-open interval from a to c, and the half-open, half-closed interval from c to b, but it's discontinuous at c. If both of the individual improper integrals, the one from a to c and the other one from c to b, if both of those are convergent, then the overall improper integral from a to b is equal to the sum of the two other convergent improper integrals. Okay, let's do a couple of examples. Evaluate this integral. The integrand is dx over x minus 1 to the 1/3, and the limits are from 1 to 2. So this is an improper integral. Why is it improper? Yeah, the integrand, the function in the integrand is not defined when x equals 1. So we cannot evaluate this the way we would evaluate an ordinary definite integral. This is improper. So we write this as a limit. Let's see, what letter are we using? I guess we're still using t. So t is going to approach 1 from which side? So this interval is from 1 to 2, so t has to approach 1 from above 1 or from the right of 1. So we write 1 with a plus sign. And then we write a definite integral from t to 2. I'm going to rewrite 1 over x minus 1 to the 1/3 as x minus 1 to the negative 1/3 dx. So we could use a u substitution, but it's really not necessary, because if u is x minus 1, then du is just dx. So we can integrate directly without applying the substitution rule. All right, so the limit as t approaches 1 from above, and then an antiderivative of the quantity x minus 1 to the negative 1/3 is x minus 1 to the 2/3. Negative 1/3 plus 1 is 2/3, right? Divided by 2/3, and then evaluated from t to 2. When we divide by 2/3, that's equivalent to multiplying by 3/2. So let's evaluate the integral. Okay, so when x is 2, 2 minus 1 is 1, so we just get 3/2 times, I'll go ahead and write it, 3/2 times 1 to the 2/3. And then we're going to subtract 3/2 times the quantity t minus 1 to the 2/3. Three halves times t minus 1 to the 2/3 is defined when t equals 1. So when we compute the limit, we get 3/2 minus 3/2 times 0, or just 3/2. Okay, so that limit exists. It's equal to 3/2. That means the improper integral converges. Okay, the next example, evaluate this integral of 1 over x dx from negative 1 to 2. So it looks like a definite integral, but it's improper. Why is it improper? Yeah, in the interval from negative 1 to 2 is the number 0, but the function in the integrand 1 over x is undefined at 0. So we're going to write this improper integral as a sum of two other improper integrals. One will be from negative 1 to 0 of 1 over x dx. And the other one will be from 0 to 2, 1 over x dx. Each of those is also improper. This is These are similar to the one that we just did. Okay, so this original improper integral will be convergent if each of those two are convergent. So I'm going to start with the one on the right. So just one other comment. If either of those improper integrals is divergent, it means that the original is also divergent. So I'm just going to focus on this one. The improper integral of 1 over x dx from 0 to 2. So we define this as the limit as t approaches 0 from above of the definite integral from t to 2 of 1 over x dx. So how are you betting? Do you think this is convergent or divergent? Okay, an antiderivative of 1 over x is the natural log of x. And we'll evaluate that from t to 2, or t is greater than 0. Natural log of 2 minus the natural log of t. So as t approaches 0 from the positive side, what does the natural log of t approach? Negative infinity. Yep. So this diverges. This is negative infinity. If you consider I'll use a domain variable t. Consider the graph of y equals the natural log of t. The domain of this is all positive numbers. So from 0 to infinity, but excluding 0. And the negative y-axis is a vertical asymptote. The graph looks something like that. So if the t-values approach 0 from the right, the natural log of t approaches negative infinity. Okay, so this one is divergent. Okay, on the next page, we have a comparison theorem. Suppose f and g are continuous functions on the infinite interval from a to infinity. So a is a finite number. And also where 0 is less than or equal to g of x, which is less than or equal to f of x, for all values of x from a to infinity. Okay, if the improper integral of f of x dx from a to infinity is convergent, then so will the improper integral of g of x dx be convergent from a to infinity. So key observation for this part A is the fact that g of x is less than or equal to f of x. So for any value of t, when you take the limit of t by letting t go to infinity of the definite integral from a to t, for any value of t, that definite integral of f of x will be greater than or equal to the corresponding definite integral for g of x. But since f of x is convergent, then so must, sort of fouling that up, since the improper integral of f of x from a to infinity is convergent, then so will the improper integral of g of x dx from a to infinity. That will also be convergent based upon this inequality. And then analogously, if the improper integral of g of x dx from a to infinity is divergent, then so will the improper integral of f of x dx from a to infinity be divergent. Okay, so let's determine if this improper integral is convergent or divergent. We don't need to find the value of it. We just want to determine if it's convergent or divergent. So do you have a guess? Like it's a coin flip, divergent or convergent? Okay, I'll show you what I would do if I wanted to determine whether this converges or not. I'm going to use the comparison theorem. Okay, so for x greater than or equal to 1, x squared minus 0.01 is a smaller number than x squared. Do you agree with me? Are we in agreement? Well, both of these are positive, and the square root function is an increasing function, so the square root of x squared minus 0.01 is less than the square root of x squared. But since x is positive, the square root of x squared is just x. Okay, what's going to come next? So in arithmetic of real numbers, if one real number is less than another, then the reciprocal of the first is greater than the reciprocal of the other. You see what I mean? So this number, the square root of x squared minus 0.01, is less than x. That means that the reciprocal of the number on the left, 1 over the square root of x squared minus 0.01, is greater than 1 over x. Or you could think of it as equivalently as 1 over x is less than 1 over the square root of x squared minus 0.01. And we know that the improper integral of 1 over x diverges. And so by the comparison theorem, since 1 over x is less than 1 over the square root of x squared minus 0.01 for x greater than or equal to 1, by the comparison theorem, I'll just sort of short this by a comparison test. This improper integral also diverges. See how that works? Okay, we can probably do the next one pretty quickly. Same idea. So on this one, for x greater than or equal to 1, e to the 2x plus x to the 3 halves is greater than x to the 3 halves. So that means the reciprocal of the number on the left, 1 over e to the 2x plus x to the 3 halves, is less than the reciprocal of the other number, 1 over x to the 3 halves. So what do we know about the improper integral of 1 over x to the 3 halves from 1 to infinity? So this is one of those p functions, 1 over x to the p. So this has the form 1 over x to the p dx, and p is greater than 1. The exponent 3 halves is greater than 1. So what do we know about those improper integrals when p is greater than 1? They converge, yeah. So these converge. So by the comparison test, the other improper integral of 1 over e to the 2x plus x to the 3 halves dx, this also converges. Okay, we're a few seconds over time, so online, go ahead and sign in for attendance. Tomorrow we'll start the test 1 review. Nicholas, right? Okay. Thank you.